On our previous video, we looked at various ways by which we actually enhance a particular radical reaction, either through the release of a gas, either nitrogen or carbon dioxide, or we actually have a target particular bond where we actually focus on a peroxide molecule where we have a specific weak bond, and this weak bond in the case is a oxygen single bond, which requires 40 kilocalories per mole, and this can actually be triggered at room temperature. So it's quite interesting to see how we need to be able to preserve molecules like this for we to actually improve the integrity of that particular molecule. Now, in this particular video, we're going to look at the two ways of radical production, and the first way is actually a thermally enhanced reaction, or on the other side we have a photochemical enhanced reaction, and in both cases we're actually targeting specific bonds or variation of bonds. Now, in the case of a photochemical enhanced process, we actually focus on also expressing the photolytic cleavage, and this particular type of reaction is actually enhanced by focusing on a particle called a photon, and that is the form by which light actually exists, and this photon must be absorbed by a molecule, and in this case a molecule which has I would say a model in this particular format. And to target this particular bond, we actually need a specific particle, which is a photon, that needs to be absorbed by this particular molecule in order for it to actually cleave its bond and form two radicals. So this actually must be sufficient in terms of the energy of this particular photon in order for this to cause a homolytic cleavage. Now, for example, we looked at ozone, which is a nitrogen double bonded with a nitrogen, and this actually has R groups attached on both sides of the nitrogen, and what we notice is that some of these particular photons can be absorbed by this particular molecule to perform isomerization, where we actually have the transitioning from a cis to a trans or vice versa, and this is kind of a competitive reaction where this particular molecule actually absorbs a specific photon energy, and this could either result in isomerization, or on the other side we actually have the formation of a particular radical, which is the cleavage of a bond where we actually absorb another energy to actually perform the cleavage of the RN bonds, and this actually results in the formation of a triple bond between the two nitrogens and releases nitrogen and formation of our two R radicals. Now take note that this actually both cases results in the absorbing of a particular photon, and to get this particular energy required is actually expressed as E equals the Planck constant multiplied by the frequency, where the frequency is actually equal to the speed of light by the wavelength. And looking at the wavelength, it's actually targeted towards exploring the two laws of photochemistry. Now, the first law is the main purpose or focus of this particular video, and this is actually that molecules must have absorbing ability for or of photons in order to form homolytic cleavage, and that is what we actually explored in this side of the video, where this particular molecule here must have the ability to actually absorb this particular photon right there. For example, looking at this particular oxygen bond, in a peroxide molecule where we have a carbon here, and on the other side we have a carbon attached right there. And what we noticed from our previous video is that this bond here actually has or requires an energy of 40 cals per mole for the bond to actually cleave. Now take note that this molecule right here must actually absorb at 300 nanometer, which is a high energy in a way. So this molecule must absorb this particular amount of wavelength, which is the energy, instead of less than 700 nanometers. So in this particular case, what we result in is that once this molecule overcomes this particular energy, then this bond can actually cleave to form our two radicals. Now on the other side, we have going for the photochemical to the thermal process. The thermal process actually involves a thermal radical generation where we actually target the cleavage of a very strong bond, in this case a carbon-carbon bond, during cracking. And this is kind of interesting because cracking actually leads to so many side unwanted products, and that is a little bit of a disadvantage in a way because we're not able to target a specific amount of bond or a specific type of bond compared to that of photochemical reactions, where you just need a particular amount of energy for a specific bond. In thermochemical process, unwanted bonds are actually targeted, and that leads to unwanted side products, and this can actually be prevented by actually using a specific radical which is called a ALBN, and ALBN is actually expressed as azo bis isobutyrol nitrile. So this particular compound actually has a carbon nitrogen bond that is really weak, and this has an energy of 31 kilocals per mole, which is the activation energy, and this is actually a low amount of energy that is required for the cleavage of the CN bond in an azo bis isobutene nitrile compound. So what the result is that once you subject this particular molecule to this small amount of energy, where we express the chemical structure to be this, and we have a CN, we have a CH3 right here, and we have a CH3 right here. On the other side we have the same thing, but on the other side CH3, CH3, CN. We target this bond, and that results in the cleavage and the formation of nitrogen gas, which is actually the driving force for the formation of a more stable molecule, which is the nitrogen gas. And this is the other product right there, which is radical on the center carbon, and we have our CH3s right there. So that's about it for this particular video, where we explore the two ways of radical production. One, the thermal process, where we generate unwanted side products due to the range of energies that is available. On the other side, we actually looked at photochemical process, which is the photolytic cleavage, where we require a photon that is actually dependent on the absorbing ability of a particular molecule. So all the same, please hit a comment down below. Let me hear your thoughts about this and many more. By that way, I can talk to you all later. Stay smart and believe in yourself.